Okay, so the next chapter that we're working on, current and resistance, is a pretty short chapter because what we're doing in current and resistance, we've already really dealt with these things in lab, and we're just carefully defining what current and resistance are and how we measure them, where they come from. So we'll just have a little bit on current, a little bit on resistance, and then we move on to circuits, or back to circuits, which we've already studied in lab. So let's start with the definition of current. I have a tendency to use capital I for current. Your book uses little I in a lot of places. But I is defined as dq dt. What does that mean? It's the rate of change of charge, but we got to be careful about what that means, rate of change of charge. When we're talking about current, we're talking about charge flow. And charge can flow through things. Charge can also flow through the air. It doesn't really matter. You can have a current flowing through the air of charges, or you can have current flowing through a wire. But let's just think about a wire. And here's a wire, right? It's just a blown up version of a wire, and you got charges, electrons perhaps, or little charges Q going through that wire. But there's a lot of them, right? There's all kinds of charges flowing through the wire. Okay, dq dt really means the total charge. So I draw little q's as in an individual charge. dq dt is the total charge that flows by a particular point in a certain amount of time, right? So you're looking down at this cross section of the wire, and we're asking how much charge flows through that cross section per unit time. That's the rate of flow of charge through a wire. That's dq dt. So, sorry, I drew this little image that you probably didn't know what it was. This thing here, I'm going to redraw it, is how we draw an I, right? So I'm just drawing showing downwards. That's an I. Crumbs, sorry. Okay, see this beautiful picture that I've drawn here of a person, and look, that is how I'm drawing their eye. It's a triangle with a circle in it, and that is typically how we draw. I'm having a lot of problems with my iPad. Hold on. How we draw an eye in physics, just to indicate what we're looking at. So we're looking at this cross section in this wire, and we're asking how much charge passes that plane per unit time, the total charge, d big Q dt. So there's a lot of little q's that are passing by. Okay. So what are the units of current? Let me go back to current. I'm going to rewrite it. dq dt. It is units of coulombs over time. Coulombs over time. Coulombs over seconds. MKS units is coulombs over second. And we define that MKS unit as the ampere, also as capital A. So that is the unit. The ampere is the MKS unit of current. Okay, I think we've talked about in lab that potential, we remember, we're going to talk about V equals IR, potential difference equals current times resistance. That's relevant here, but not just yet. So let me just remind you that potential is the potential to push current through something that has resistance R, or potential to push current through anything. So potential is not is not the moving charges. The current is the moving charges. And we talked about in electricity, what is dangerous is pushing charges through you, right? And it's because you have a resistance. If you try to push charges through you, then you burn things, and you damage things. And you also, if you have charges and your body runs on very small amounts of electrical current, moving charges through you can mess up those electrical currents and can stop your body from functioning correctly, stop your heart, for example. So current is what's dangerous, not potential. Potential is only dangerous if it's strong enough to push the current through you. But current, the movement of charges through something, is what actually does the work, right? What actually does the damage? What actually does the work in an electronic device, which is good, or what actually does the damage when current passes through you? Okay, moving back to definition of current. We can take the definition of current and rewrite it. So since I is equal to dq dt, And that's, again, the amount of total charge that passes through a certain plane in a certain amount of time, in a certain cross-section in an area in a certain amount of time. We can rewrite that as dq equals I dt. And what that does, if we integrate both sides, that tells us the total charge that passes through a certain area in a certain amount of time. So we could go ahead and integrate from 0 to t and find that the total charge is the integral of the current times dt. So for example, if I pass a current of 3 amps. What's a big current and what's a small current? We've talked about it in class, in lab, but let me just remind you that a household device household devices typically can go up to 20 amps, which is why you have 20 amp circuit breakers in your circuit breaker box. And a typical device might be a couple amps, but an electronic device might be milliamps, might be tiny amounts of current. Well, tiny, it's all relative. Because what's bad for you, if you actually pass milliamps of current through your heart, that's enough to stop it. It's just that your skin has a very high resistance. So a milliamp of current is typically not gonna, if you have something pushing a milliamp of current, it's not gonna push it through your skin into your heart. But a milliamp is a couple milliamps or 10 milliamps is enough to stop your heart. But typically currents can go up to a couple of amps in your house. Therefore, they are dangerous. And in a lab setting, it's not unusual to get currents of upwards of 100 amps, which is super dangerous. But anyway, so just in terms of the size of things. So unlike a farad capacitor, which is very, very unusual, a couple amps is not an unusual amount of current. Okay, so let's say that we have a wire. So let's say I have a lamp plugged into a wall, and let's say that there's 2 amps, although that would be a lot for a lamp, but whatever, that's not overly too much. Let's say that there's 2 amps of current equals 2 amps traveling through that wire. If I leave the lamp on for 10 minutes, how much charge has flowed from the wall receptacle to the light bulb? Okay, I've written it down, how much charge flows to the lamp in 10 minutes of use. And so we would just say Q is equal to the integral from 0 to 10 minutes of the current, which is 2 amps times dt. And actually, you didn't really need an integral here because it's not a varying current. It doesn't vary with time. So the integral, we can do the integral. 2 amps is just a constant, right? 2 amps. I'm just carrying the units. And so we've got the integral of dt from 0 to 10 minutes. And the integral of dt is just t because there's nothing else to integrate. And so we get, Again, I'm carrying the units with me, so 2 amps. A is not a variable in this. 2 amps times t from 10 minutes to 0, evaluated from 10 minutes to 0. It really is just 2 amps times delta t, which is going to be 2 amps times 10 minutes. And now, be careful. We want to keep MKS units because amps is coulombs per second. So it's going to be 2 amps times 600 seconds. And so that is 1,200 coulombs of charge. 1,200 coulombs of charge flow to the light bulb in 10 minutes. Okay, any questions? Well, good. All right, moving right along. Trying to come up with a joke, but I can't think of a joke currently. Haha, get it? Pun, haha. Okay, let's talk about the direction of the current. Just to make sure, to review, that the direction of the current is the direction that, when we talk about the direction of current, when we talk about direction of current in a circuit, is the direction that the plus charges would flow. So we can talk about the direction that minus charges would flow, but that's not what we talk about as the direction of current. The direction of current is the direction that positive charges would flow. When we draw a power supply, there's always a positive and a negative. And if it's a battery, then the positive is the big plate, and the negative is the little plate. And the current is the direction that the positive charge would flow. So the current in the circuit shown here would flow clockwise. the current flows this way through the circuit. The pluses go from the plus plate to the minus plate. In reality, you know that minus charges are more typically the things that move in a circuit or in any situation. Plus charges can move, but minus charges move. And so in reality, the current, the minus charges go the other way, but that's equivalent to the plus charges going in the clockwise direction. Okay, that's the direction of current. The other thing to review is that current is a conserved quantity. Current is the movement of charge, and charge does not get used up. It gets slowed down by resistances, but it doesn't get used up when it's creating energy, when it's creating light in a light bulb, for example. So current is a conserved quantity, and so that brings us to the junction rule, right? So that if you've got current flowing and it splits at a junction, right? Let's just say we have two resistors or something like that. Then you have I1 going this way and I2 going this way. And because it's a conserved quantity, then I is equal to I1 plus I2. Whose law is that, or whose rule is that? Oops, that doesn't look like I1. I see it's because I combined the arrow with the one. I1. Okay, whose rule is that? It's Kirchhoff's junction rule. Kirchhoff's junction rule. I'm not sure that it really needed to be named after Kirchhoff, but it's like Ralph's junction rule. Anybody could figure out that if charge is a conserved quantity, that when it comes to a junction, it must add in that way. Okay, here's another question about current. Let's say we have a time-varying current, right, in an AC circuit, for example. Let's say, which really is what we have with our lamp. That's an AC circuit, so it's time-varying. And the time-varying current goes as some I0, some current I0 times sine omega t, where omega is the frequency and t is the time. And ask how much total charge passes through the device. So the device meaning the resistor here, which might be a lamp or whatever, how much total charge passes through the device for each cycle of this AC circuit, each cycle of current, because the current is alternating. Okay, so how would we calculate that? Or can you even guess it? I'll give you a hint. Something you could guess. But anyway, let's go ahead and calculate it, because Q is the integral of I dt. Now I is time dependent, right? So Q is the integral of I0 sine omega t dt. And so we can pull out the constants. It's an integral. So the constant here is I0 is that amplitude of the current, integral of sine omega t dt. I haven't told you what omega is. Omega is the frequency, right? We in lab is the angular frequency. In lab we set the frequency generators at 1,000 hertz or whatever. Coming out of the wall it's 120 hertz. And remember that, just as an aside, omega is 2 pi f. So this is the 1,000 hertz, 120 hertz wall outlet. So it doesn't matter what omega is, because what I'm asking is for one full cycle. So the cycle depends on omega. And so in order to answer this question, how to do this integral, is we do need to know the limits, right? 0 to t. One full cycle is one full period. So we need to go from 0 to t, where t is the period. And so since omega is 2 pi f, therefore omega is 2 pi times 1 over period, and so therefore period is equal to 2 pi over omega. So we're integrating from 0 to 2 pi over omega. So let's go ahead and write this out. Q is equal to I0 integral of sine omega t dt from 0 to 2 pi over omega. Okay, so let's do that integral. I0, what's the integral of sine omega t? So most of you at this point know how to do the integral of a sine, but if you don't, what do? You look it up in an integral table. You look it up in Wolfram Alpha. You look it up in, what is that? I can't remember, the integral lookup.com or whatever it is. But anyway, you do the integral of sine, and the integral of sine omega t is minus the cosine omega t divided by the omega, because the derivative of the quantity in the brackets must equal sine omega t, right? The derivative of that the derivative of the cosine is minus the sine, and then you have to take the derivative of the inside, which gives you an omega. So that's the integral. Look it up if you don't know it. Do it by substitution, whatever. But there we go, and we have to evaluate the integral from 0 to 2 pi over omega. So what do we get? We get I0 over omega minus I0 over omega times the cosine of omega times 2 pi over omega minus the cosine of 0, which equals minus I0 over omega times the cosine of 2 pi minus the cosine of 0, which equals 0. What? Wait a second. Now, how can I power a lamp if I pass no charge through it? How does that work? Did we do it right? Yes, we did. We did it right. And that's what I meant by you might be able to guess the answer. And I even indicated it by drawing the arrows of the current, because what an AC power supply does is it pushes current, let me find the right color. It pushes current one direction, and then it pushes it the other direction. So the net effect is that no net charge passes through. But that's over time. At any instant, there is charge passing through the device. It's just sometimes the charge is going to the left and sometimes the charge is going to the right. The net effect is that no net charge passes through, but we have, let's say it's electrons that are passing through. We initially have electrons passing through to the left, then they come back through to the right. In both passes, they're powering the device. It's not like in one pass it powers it and the other pass it unpowers it. In both passes, they power the device. So the net charge passing through the device is indeed 0. Doesn't mean that no charge passed. Well, it means the net charge of 0 passed through, but charge was passing through all the time, powering the device. Interesting result. Okay, good enough for today. See you soon.